Hello Leetcoders. Today we are going to solve day 24 problem in the July coding challenge. So without further delay, let's get started. Given a directed acyclic graph of n nodes, find all possible paths from node 0 to node n-1 and return them in any order. So we basically are given a graph in this form where each of the element in the graph in the list is representing the connection for that position or index and the node. So in this case, for example, the first element at index 0 have a connection to node 1 and node 2, which you can also see in the explanation below. The element 1 has connection to 3. So 1 is connected to 3. Element 2 has connection to 3. Element 3 do not have any further connections. So this is the graph that we are given. We need to find all the possible paths using which we can reach to the final node. In this case, node 3. So clearly you can see you can start from 0 and then go to 1 and then 3, and you can also start from 0 and go to 2 and then go to 3. So to solve this problem, we can use both depth first search and also breadth first search. I am going to show you both the solutions. At the end of the video, I will also explain you which is more efficient and why. So without further delay, let's see how DFS works first. So let's say we are given a graph which is something like this. We are just taking the example that we are provided. And then there is a 3 node, something like this, right? So now in this case, if I do a DFS, which is depth first search, so I would first go to 0th node because that is my starting point. From 0, I can either go to 1, I can also go to 2. So I took a path, which is one path, and then I first traverse all of the nodes of 1. So from 1, I can go to 3, and then I cannot go anything. So after this is completed, I again come back to this node 0, and I would see, okay, I still have 2 in my path which I can visit further. So I go to 2, and from 2 I will go to the neighbors of 2, which is 3. So my path will become 0, 1 and 3, and 0, 2 and 3. So this will be the output that I will return. Now let's just write code for this first, and then I will also explain you the BFS approach. So first we are going to write the function that will do DFS. In the function I would require a graph. I would also require the current node. I would also require a path variable to track, and then I would also require the output to save the path which have been completed. So if we have reached at the destination node, we would want to save that path to our output list. So that is our output is doing. So now our base case would be if node is equal to our final node, which is the length of the graph, -1. Then I would simply append the node to the path and put that path into the output list, right? Now, if that is not the case, I would want to traverse all of the neighbors of the graph. So, for a neighbor in graph of node, so basically these are the neighbors, like 1 and 2 are neighbors of node at 0. 3 is the neighbor at node 1. 2 is the neighbor at node no 3 is the neighbor at node 3. So this I will get by using this loop. And for all of these loops, I will again do DFS. So I will recursively call this function till I will reach the final destination. So I will pass the graph, I will pass my node, which will be neighbor in this case, and then I would pass my path will become path plus whatever is my current node that will be added to the path, and I would also supply the output for the path to be stored in this. So this is my DFS function. I would call this DFS function from my root function like this. So I actually do not need the graph here because in Python the closure can read the value. They of course cannot change it, but they can read the data. So it will be one less number of argument in the function. So I do not need to pass a graph here. I can simply pass 0 because that would be my starting node, and my path will be an empty list in the start and output. Then I will simply return the output. So let's try to run it. This worked. Let's submit this. This got accepted. Now let's just also see the BFS approach or the breadth first search approach. So for the BFS approach, the explanation would be like this. You would first, instead of like traversing, let me just go to BFS. In BFS, you would first go to each of the neighbors of the starting point, and then from those neighbors, you will go to the next neighbor. So BFS is generally used for finding shortest paths because uh, given a source and destination, BFS can find it much quicker because you will not go much deeper into the graph, and you would essentially traverse all the neighbors first before going to the depth. So in this case, I will start with 0 node, and then according to BFS, I would traverse the neighbors of 0, which are 1 and 2. Now 1 and 2 will be pushed to the queue. I will traverse 1 first and then see, okay, 3 is there. As soon as I will get 3, I know, okay, this is my destination node. So I would I would make a path. So when I am traversing this in the queue, so in the queue I will store the path. So if my path, initially the path will be 0, then after I will travel 1 and 2, the path will have, the queue will have two element which will be like this, 0 1 and 0 2. Now I would pick the last item in each of the element from the queue, and then I would do further like find the neighbors of those elements. In this case, one has a neighbor of 3. So the next item in the queue would go like this. And for this, the next item in the queue will be pushed like this. And now I will pop both of the items from the queue in the next iteration. And I would see, okay, the last item is 3, which is my destination. So I would simply append all of the output into the output list. So that is how it will work. So let's just write code for this. I am commenting out the DFS approach first, and then let's write the BFS approach. For BFS, I would need a queue. I'm I'm using a simple list for queue. You can also use a DQ. So, and I am also storing the length, which is, or let me just say it as target, length of graph -1, right? Now let's start our queue operation. Our queue will have 0 first. We will also have an output which will be empty. I am storing the list of paths in the queue. So queue will be having the paths in it. So I will, for each of, for the length of the queue, I would pop the items from the queue. So queue.pop, this will give me the path. Now I would find the last item in the path. And now for this current node, for this last node, I need to find the neighbors. So first I need to check if last node is equal to my target. I would simply append the path into my output. If that is not the case, I would actually, I will continue. If that is not the case, I would traverse all the neighbors of the graph and for each of the neighbors I will append so I would append that neighbor to the path and then put that path into the queue. So I am doing this like this, path plus neighbor, at the end I will return the output. So this is basically kind of level loaded traversal. Yeah, so this is working fine. Let's submit this. Yeah, this got accepted. This is slightly better than DFS. When I tried solving this problem, this was showing me somewhere here. So this graph is pretty much like, I don't know how it works, but let's see. So I think BFS approach would be much faster here because you are kind of solving the problem of shortest distance, and you can avoid the overhead of coming back to the root node and then traversing all of the nodes again, which is done in case of DFS. So BFS would be the way to go for this question. I hope you now have better clarity of both of the approaches and how this works. Please don't forget to like this video and subscribe the channel for more such content. I will see you in the next video.